Hey guys, so this video will cover energy and calorimetry. So what is energy? Energy is simply the ability to do work. So in terms of reactions, kinetic energy, which is the type of energy that we're usually talking about when we talk about chemistry, even though it works hand in hand with temperature and may lead to phase changes, it does not always affect the temperature, and you'll get to see this more later when we're talking about heating and cooling curves and those kind of things. But there's a little diagram here that might help you better understand it in terms of states of matter. So as you can see, the gases have more kinetic energy, and as the arrow indicates, as you move down from gases to liquids to solid, that kinetic energy is decreasing. So the particles are not moving as fast, and in gases the particles are translating and moving really freely. But then once you get to liquids and solids, it's more vibration that's happening because of the decrease in kinetic energy. And bonds are also another huge example of how energy is related to chemistry. And it's making versus breaking bonds. And a lot of that has to tie in with endothermic and exothermic reactions, which we will learn more about pretty soon. So when we talk about heat versus temperature, we really want to stress that they are not the same thing. Heat is the flow of thermal energy, and temperature is essentially the speed of the molecules. And you will see that even though they have a positive correlation, meaning they do affect one another, you can still add energy into a system without changing the temperature. And we will look at that later on with heating and cooling curves. But for right now, when we talk about energy exiting or entering system, we're talking about two different types of energy profiles, or essentially two different types of reactions. The first one being the endothermic reaction, where the system needs energy. It doesn't have enough energy to help the reaction proceed, so therefore the system has to absorb energy from its surroundings. Now, on the other hand, you have the exothermic reaction, and this is where you have an excess of energy left over once the reaction has been completed. So where does that excess energy go? It goes from the system to its surroundings. So to better understand the difference, you kind of have to look at actual processes that these apply to. So first of all, when you look at photosynthesis, for example, the plant absorbs the sun's energy in order to produce glucose. So since that energy is being absorbed by the system from its surroundings, it is endothermic. Now, on the other hand, when you look at, let's say, a candle burning, that would be an exothermic reaction because energy is being released in the form of heat from the system. So that's why when you put your hand over a candle flame, you can feel the warmth, you can feel that heat being emitted because it's leaving the system. So therefore it is exothermic. Now we're going to take a look at how these two different types of reactions are graphically represented in the forms of energy profiles. So this one is an endothermic energy profile, and you're not always going to have these cute little labels here to help you identify what it is. So the way that you would tell that it's endothermic is that the y-axis, which is your energy, if you start off at a plateau that's lower and then you hit that curve during the reaction and then it plateaus again where the product side is labeled, if that product side is higher up on the y-axis, it means that energy has increased, which means that the system or the reaction has taken in or absorbed energy in order to make that reaction work. So since it's absorbed energy, we know that it would be endothermic. Now, when you're dealing with it in terms of equations, when you don't have a graph to look at, you need to know that you're actually looking at it in terms of energy in the surroundings. So there's a difference between the system and the surroundings. The system, such as an ice cube melting, for example, you can't really measure the processes happening inside the ice cube while it's melting. It's kind of impossible to measure. So really what you're looking at is the surroundings. So if that ice cube is in a glass of water, you're really measuring the temperature of the water because you know by the law of conservation that the energy lost is equal to the energy gained. So if the water gets colder, you know that the ice cube has taken in energy. So that's how you would tell. So for this, you would add energy to the reactant side of the equation because the reactants are absorbing that heat. So when you have an endothermic reaction, delta H, or enthalpy, which you guys will learn about in another video, is positive. And that's also the same thing as heat, which we're going to relate to calorimetry in just a second. And the reason that that makes sense is because heat is positive because of the energy gained by the system, because it is endothermic. So this one is an exothermic energy profile, and as you can tell, it's pretty similar to the endothermic one, except for the initial and final points of those plateaus. So your initial plateau, where the reactants are, you can tell that it's higher up than the final plateau where the products are. And that's because it has lost energy. The energy on the y-axis has decreased because it is exothermic and it is giving off that energy. So for an exothermic reaction, energy is going to be added to the product side of the equation. And this makes sense if you think about it, because the system itself is emitting its energy. It is giving off heat. And by the law of conservation of energy, the heat gained is the heat lost. So all of that energy, all that heat is being emitted out to its surroundings. So therefore, the reactants are losing energy and it is going towards the product side of the equation. And delta H, or enthalpy, for this would be negative because it has lost heat.